Thank you, and good morning. So I'm going to, first of all, my name is Oskar Painter. I'm director of quantum hardware at AWS, and I'm going to be joined this morning on the stage by Richard Moulds, who is our general manager of the Bracket Quantum Computing Cloud Service. So I'm going to begin by telling you, introducing to you our own internal quantum hardware effort. I'm going to do this at a relatively high level, with a goal, again, of introducing you to this fact and with the hopes of engaging partners in the future that want to work on developing this sort of long-term roadmap that we have for quantum computing. So after I finish, I'll hand things back to Richard, and he'll present the bulk of the talk, where he'll be talking about what we're doing today at AWS to work with customers and to bring quantum computing to our customers. So let me begin by sort of level setting what we're trying to do at AWS in the quantum computing space in quantum hardware. So let me start by talking about our long-term goals, which is to really build a practical quantum computer that can bring significant quantum advantage on commercially relevant problems to our customers. And I'm just going to throw out here 4 rules of thumb by which we sort of evaluate what such a practical quantum computer might look like. And so one can quibble about some of these numbers, but ultimately we really have to recognize the fact that in order to run circuits that are with depths of 1 billion, which we think for known problems of commercial interest, and to do that over 1,000 or 100 or 1,000 logical qubits, we really need to reduce our error rates down to about 1 e to the minus 12, and that's a 9 orders of magnitude error rate gap. And so I think our approach at AWS is to embrace that challenge from day one, to really work towards developing quantum computing hardware that can realize these sorts of error rates. So our guiding technical principles, so what we're really, at a high level, how we're defining our roadmap, is really around, in order to close that error rate gap, is really built around the idea of quantum error correction. So we are thinking about quantum error correction right from the beginning, thinking about how the choice of physical qubits will impact the architectures that one can employ, and then ultimately how this might impact things at the classical control stack and the software control stack. Ideas like real-time feedback, distributed across a large number of physical qubits. These are really technically challenging problems, and you need to start thinking about these things really early on. So here's just a rough development path that one would take in trying to implement quantum error correction in a fault-tolerant quantum computer. This is, we're really early on as an industry in this development, but it's a really exciting phase as well, where we're starting to, realize quantum systems at the logical level, logical qubits, that are starting to, perform close to or even beyond the performance of the underlying physical hardware. We think that, over time there'll be, some of the earlier applications will be where we have 100 or 1,000 of these logical qubits with error rates of around 1 e to the minus 10, 1 e to the minus 12. Those will be rather targeted, applications, maybe in material science and in, small-scale material modeling, in chemistry applications, for instance. And we'll have to do further scaling, where we look at going beyond that and scaling up the system both in the physical size, but also in the speed at which we can clock these systems. Along the way, this development at the logical level will require improvements that will be driven by improvements at the physical hardware level. And maybe more importantly, I think, we'll also need to really focus on algorithmic development as well. So this will be critical not only to develop new algorithms that these performant quantum computers will be able to implement, and so to increase the possible application space, but also to adjust to the evolving architecture. So there's going to be a tremendous amount of evolution in the way that we build quantum computers, and both at the processor level all the way up through the whole stack as we start to implement an error-corrected quantum computer. And so we need to be able to think about how algorithms can adjust to that and make use of that evolution. So I'm just going to end here with a few personal thoughts and observations, and then hand things over to Richard. And these are things that I've learned as I've been at AWS for the last few years that weren't entirely obvious when we first started this project. So I think, I'm a scientist by training. I've worked in academia for most of my career, and when I look at the technical problems that that we need to overcome, my reflexive reaction is to try to solve all of them. And as we've been going on, and as we've been doing this more and more, it's become very clear that we're going to need to partner and with other companies and really only focus on the core things that we need to do, the things that others don't want to solve or that we are in a particularly good position to solve. So there's going to be a lot of partnership at AWS in terms of this building out our quantum computers. Second thing is that there's a tremendous amount of development and innovation that we can, that needs to go on in the infrastructure that will go around these quantum computers. And at AWS, this is something that they've done particularly well with regards to cloud computing. And I've learned a lot in my short time at AWS, and see a lot of opportunities that really has opened my eyes in terms of the opportunities that in terms of this infrastructure innovation and development needs to occur while we're developing the hardware. And then finally, I started out by saying that there's this huge 9 orders of magnitude gap. I want to say that, I'm at this point, 3 years in, I'm much more confident, not less confident, that we have a real path towards a viable quantum computer, even at that sort of scale and that sort of error rate. So, I think we're up for the challenge at AWS, and we're really interested in talking to others that want to take a similar path towards developing quantum computers. So enough for me. Let me hand this over to Richard, and he's going to tell you about what we're doing today with customers in the quantum computing space.
Thanks,
Go, Richard.
Hey, everybody. Seems amazing that a whole year has flown by since we were here at Q2B last year. It's astonishing. I know some of us in the room have been to 3 conferences now in 4 weeks, so we're heading to the holidays, hopefully. All right, so I'm Richard Moulds. I'm the General Manager of Amazon Bracket, and my team plans, builds, and runs operationally day-to-day the quantum computing service of AWS. And most of this session is sort of reflecting on the last year, but also thinking about some of the key themes and obviously trying to always tie it back to what customers are telling us on a day-to-day basis and what we're learning as we go along. I often get asked, how do we see ourselves in the industry? And the term that always comes to mind is a sort of public square for quantum computing. We launched Bracket 3 years ago. It's been generally available now for 2.25 years or so. So we've learned a lot over the process. And it's really about bringing folks together and trying to accelerate innovation. We're not trying to push a particular technology. It's not about us. It really is sort of about you and trying to just move the ball forward. And that's pretty much the role that AWS plays in lots of industries. Think of emerging industries like robotics, game technology, the dear old metaverse, IoT. AWS has played a foundational role, really just trying to generate momentum and move it forward. And there's sort of general tenets that we have when we think about these markets. First of all is make the resources, typically the compute resources available for customers, deliver a consistent set of tooling, provided as part of a platform that partners can build on, and fundamentally just remove the barriers to adoption so that folks can get started easily. And that's exactly what we're doing with Brackets. What we hear from customers day in, day out. If we can deliver these 4 things, then we think we've provided a service. So start by the first bullet point, diverse set of hardware. So customers tell us over and over again that they do not want to get trapped into a single technology silo. It's way, way, way too early. This stuff's very different. They don't want to hear from a lone voice. They really want to try this themselves, and they want to be able to play the field. So our goal is to offer multiple examples of all of the major modalities that are available in this industry, and just make it easy. This year we launched 3 new devices from 3 new partners. Really exciting. We started with the Lucy device from Oxford Quantum Circuits earlier in the year, our first European-based quantum hardware. Soon after, launched the Borealis device from Xanadu, which is the first time that it's been possible publicly to verify a claim of quantum supremacy. So again, really exciting and different type of device. And then just recently we launched the Aquila device from QEra, which I think is pretty much the first publicly available device based on neutral atoms. Always open to new partnerships. I know a lot of hardware providers and aspiring providers in the audience, so always willing to hear about ideas to join Bracket. I wanted to highlight a little bit just QEra. It's a really interesting device. It's not a general purpose machine, but it's got some very interesting properties. And most importantly, it launched a new programming paradigm on Bracket analog Hamiltonian simulation for simulating physical systems and trying to knock down a subset of certain optimization problems. 256 qubits, represented built on rubidium atoms in an array. It's a flexible array. It's not tied to a particular geometry, and a continuous quantum evolution based on pretty strong interactive forces. There's a fireside chat at 12:30 today with Alex, CEO of QEra. So if that's interesting, please go along. I heartily recommend it. So in addition to providing compute resources, it's also about tooling, because at the end of the day, resources are sort of useless if you can't use them. So we hear from customers that they want a consistent set of tools. They don't want to be learning new tools for different devices. They want to try and apply the common tools across as many platforms as possible. And they want to work at different levels in the stack. A lot of those tools obviously are focused these days on combating errors, either mitigating errors, reducing errors, or just dealing with the presence of errors. And a lot of customers want to dive right down in the stacks. One of the things we've learned since launching Bracket, you would think everybody would want to abstract away from the hardware. But these are still early days, and actually folks want to get their hands dirty, roll their sleeves, and go play on the actual hardware. So we launched Bracket Pulse just a few weeks ago. Allows you to actually control the microwave pulsing on superconducting circuits. It works with the Rigetti hardware and the Oxford Quantum Circuits hardware, fundamentally to try to optimize gate operations. I wanted to highlight some early results. So this is literally 3 or 4 weeks' work. 3 partners were pretty heavily involved in the preview of the feature before we went GA. Wanted to highlight results from Kedman, one of our partners who have been trying to optimize the ISOP gate in Rigetti. A shocking amount of GPU resources to run their characterization and gate optimization systems, but already able to reduce coherent error by a factor of about 3. Also wanted to highlight a joint blog we put out with the folks at Supertech, part of Colquanta Inflection, earlier this week, about how they're using dynamical decoupling to reduce errors. And then just on Monday, Q-Control launched FireOpal, which again leverages Bracket Pulse to suppress errors. So again, check all those 3 partners out. I haven't got time to dive into the details, unfortunately. In terms of higher up in the stack, in terms of tooling, a year or so ago, we launched a product feature called Bracket Hybrid Jobs, which is all about trying to make variational algorithms and other hybrid algorithms just fundamentally easy to use. That's the sort of central theme of the NISQ era. What can we do in the presence of errors just to do better with current hardware? Bracket Hybrid Jobs orchestrates and manages classical and quantum resources for you, so you don't have to. You just provide a container, and we do pretty much everything else. And most importantly, it grants you priority access to hardware. So once your job starts running, you pretty much own that device until your job finishes. Now, quantum hardware, limited availability during the day in some cases. So a lot of the heavy lifting for hybrid workloads is based on simulators and very tightly tied to Penny Lane. So again, a year or so ago, we doubled down on our relationship with Penny Lane as our preferred toolkit for programming variational algorithms. We launched a couple of features. Back in the summer, we launched an embedded simulator capability working with NVIDIA alongside Penny Lane to deliver GPU-based, really high-performance GPU-based simulation in the classical stack. Dramatically reduces the runtime of the process. And then, in fact, just today, we are launching gradient descent result type for SV1 simulator, a primary state vector simulator, which again dramatically reduces the number of tasks that you need to submit if you're calculating gradients. So both focus on reducing runtime and fundamentally triggering innovation around variational algorithms. Okay, we talked a lot about delivering innovation through more hardware types, through more tooling. Now I want to pivot a little bit and talk about the platform itself and how we see Bracket and how we see Bracket as playing a role within AWS and what our partners are doing to really bridge some of these systems together. So customers tell us that they want a platform that they can build on. You know, they don't just want to play with a single device. They really want to build solutions. A lot of our solution provider partners, you know, ultimately want to monetize their intellectual property and actually see Bracket and AWS as a route to market. So some customers love the richness of AWS. If you're a large corporate customer, then you know there are security issues and compliance issues that are actually mandated that get delivered through AWS. But we have to be realistic, and for some researchers that are not familiar with the cloud, you know, AWS can be an overwhelming environment to live in. Obviously, we spend our waking hours trying to make it easier, but it's been great over the last couple of years to see a set of partners really emerge that are trying to really shift the user experience associated with Bracket and to take that experience and mold it around particular customer requirements and personas. So folks like Strangeworks, I'm sure you're familiar with, very strong community-based provider providing access to technology even beyond those available through Bracket and delivering really important functionality, like, for example, cost tracking and usage management and limits. Just to make sure folks just don't get into trouble by overextending themselves with some of these, which can be relatively expensive resources. Cubase is another great example. Really simple to use, sophisticated platform for running large events, hackathons, training events, etc. Classique. I'm sure many of us to this day are still wearing their socks, and real focus on developer environment targeted at algorithm development. But making stuff easy is one thing. Super critical, obviously, in an emerging market. But a lot of our customers and partners come to us saying they really want to leverage AWS as a broader platform. So not just thinking about Bracket in isolation, but thinking about how they can connect together the quantum capabilities of Bracket with the classical capabilities, extended classical capabilities of AWS. A lot of our software partners are trying to take customers on a journey. You can't. It's a tricky business model to try and entirely focus your output on quantum capabilities. Customers want to solve near-term problems, but they want a path towards involving and integrating quantum as it becomes a more productive technology. I wanted to highlight good chemistry. Great example of a company that has built a classical computational chemistry service in AWS, leveraging a ton of resources. But now with the launch of the Tangelo toolkit, able to integrate quantum compute resources into that chemistry workflow. Great example for if any of you at reInvent last year, I used the last week rather, I used the conference. They explained an experiment they've done with Accenture and Intel using 1 million cores, 1.1 million cores, to go after some of the environmental impact of PFAS molecules. So this, things like Teflon, for example, stuff that never breaks down in the environment, nightmare to get rid of. Made some real progress, some fascinating videos of a man talking about how good chemistry have leveraged that solution. But there are other folks, folks like QCware with Forge, Pascal, Multiverse, for example, all using the classical components of AWS with the quantum capabilities of Bracket together to solve problems. Going even beyond that, just solving problems is fantastic, and building solutions that tie to particular problem areas is of course very exciting. It's what we're all here to figure out. Tracks galore at this event talking about it. But at some point we have to bring quantum computing to entire new industries. It's not just about compute resources, it's actually about integrating services. And a great example of that, I think, is bringing quantum computing eventually to the world of high-performance computing, HPC. It's already, obviously, HPC is a huge deal in AWS, the customers that are pushing the limits of classical compute are attracted to the cloud because of the elasticity of the compute resource, the ability to effectively infinitely scale. It seems logical to me that the companies that will benefit from quantum computing first are the companies that are running out of runway in using classical computing now. So, for example, the work we've done with Agnostic, with their covalent solution, I think shows a real direction towards the future. Not only are they bringing transformative capabilities to what is a pretty legacy industry in terms of workflow management and orchestration, but they're fundamentally from the outset providing mechanisms to bring in quantum processing within existing HPC workloads. We are going to struggle as an industry if we expect the rest of the world to come to us and our vision about how you do stuff. We have to find ways of bringing quantum to the existing supercomputing communities and existing workflows, tools that they already have in place. So Covalent, I think, it's a great tool. It's an open source product. If you haven't checked it out, check it out. Integrates with existing HPC services in AWS, like AWS Batch and AWS Parallel Cluster, as well, of course, as Amazon Braket. Okay, so we've got resources, we've got tooling, we've built an amazing platform that works at various different levels. Now we've just got to get started. I don't have time to talk about the myriad of tools we have to enable you to do that. And we're all, these days, post-COVID, of course, used to looking at menus on QR codes. So here's a bunch of QR codes. We have a phenomenal credit for research program. AWS, in driving these various new emerging industries, has established a strong record in helping academics really dig into some of these technologies. So if you have an amazing research project, you can apply for credits, not just on Braket, but credits across the AWS environment. Just on Monday last week, we launched an algorithm library just to help you get started, help build on the shoulders of giants. Check it out. If you're a Qiskit user, I know there's a lot of Qiskit users in this industry. Tremendous amount of work done in that area. We have a provider. That community has generated a provider to enable you to translate that work and run it easily on Braket. If you're interested, you can download it. Blog channel, I mentioned a couple of blogs that we put out already just this week. One this morning with Continuum, talking about how their Enquanto solution is leveraging AWS in the context of a use case we tackled with BMW around fuel cell efficiency. And if you're new to this space, I imagine there's a variety of folks here that are just trying to figure out what is it all about and when can I get started. Every month we run a free hands-on workshop, bringing some specialist speakers. If you want to sign up for the next one, which I think is December 16th, you can do so there. Anyway, I'm going to wrap up. It really isn't about us. Like I say, we're not trying to push anything in particular from a technology point of view. It really is a gathering space. We really do think of this as a public square. It's a cloud service. We live by the cloud tenants that relate across AWS. No subscriptions, only pay for what you use. A lot of people talk about offering a cloud quantum service. If they use the word subscription, then it's not really, okay? Cloud services are on demand, no subscription. We try to adhere to the fundamental tenets of what cloud computing is all about. Anyway, with that, I'll say thank you.